Today we are explaining the paper on the direction of RLVR updates for LLM reasoning identification and exploitation.
Start with the core claim.
The paper says the key clue is not only how much the token distribution changes after RLVR, but which direction each token is pushed. The authors turn that directional view into one diagnostic into practical tools. A test time extrapolation rule and the training time rewriting rule.
Direction of change sounds important, but direction of what exactly?
They define a sign token level log probability difference between the final RLVR model and its base model. They call that quantity delta log P. Positive values mean RLVR boosted a token, and negative values mean it suppressed that token.
Why was that missing from earlier analysis?
Earlier work had already noticed that RLVR updates are sparse, using entropy, KL divergence, or gradient concentration. But those views mainly measure magnitude. They can say that a token changed, yet they do not cleanly tell you whether RLVR is actively favoring that token or pushing it away. The paper writes that directional idea directly has a difference between the RLVR log probability and the base model log probability.
How should I interpret that equation when I see it on the board?
Read it as a sign comparison, not just a distance. Delta log P marks the tokens where RLVR really changed the decision rule, and the sign tells you which side of the base model the new policy moved toward. Once they plot the metrics, the contrast becomes visual.
What is the first thing to notice in that plot?
Only delta log P cleanly separates tokens generated by the RLVR model from tokens generated by the base model. Entropy and divergence cluster near zero for both. Delta log P instead forms directional tails, which means it is exposing where RLVR is helping reasoning and where it is pruning weaker choices.
And how concentrated are those important positions?
They are very concentrated. In the replacement experiment, delta log P reaches RLVR level accuracy with about 10% of tokens swapped, while the other metrics need more substitutions. So the paper is not claiming everything changes. It is claiming a small set of tokens carries most of the reasoning gain.
Why would such a tiny fraction matter so much during training?
Their gradient lemma answers that. The update size scales with 1 minus the token probability.
So where tokens receive disproportionately large learning pressure?
Exactly. The gradient plot shows that low probability tokens, even though they are sampled less often, carry most of the gradient mass. That gives a concrete mechanism for why RLVR ends up sparse training keeps spending its budget on a small set of high-impact tokens. The paper then closes the loop with a second plot. The tokens with larger delta log P are also the low probability ones. So the tokens that dominate learning are the same ones that later show the strongest directional shift.
How do the authors turn that observation into a better decoder at test time?
They define an extrapolated policy that starts from the RLVR model and moves a little farther along delta log P direction. Gamma controls how aggressively to push, and the normalization term keeps it a valid probability distribution.
Why do they apply that only at selected positions instead of everywhere?
Because most positions barely changed under RLVR. A global push would distort well-calibrated tokens. Their rule gates only the strongly negative delta log P positions, where there is evidence that the base model still underweights reasoning critical tokens.
Does that selective extrapolation actually beat the original RLVR model?
Yes. On AIME24, the extrapolation curve beats the plain RLVR baseline across SOAR's E30B, GIPO30B, and uni-reason 14B when the gates are matched. The paper also shows a concrete DIPO example. Direct extrapolation on the RLVR model lifts average at 30 from 50 to 0.50 to 55.31 with a 5.2% intervention rate. Then mostly Plato said heavier intervention. The practical message is to amplify only the small set that matters.
And what is the training time version of the same idea?
Instead of changing the decoder after training, they changed the advantage during DIPO training. Equation 8 multiplies the advantage by 1 plus alpha times 1 minus the old policy's token probability. So lower probability tokens automatically receive more weight.
What do the benchmark numbers look like for that rewriting rule?
The authors compare against two earlier rewriting baselines, called PPL and Dominate. Their method gets the best average at Fertito score at 43.75, ahead of 43.11 and 41.38. On AIME24 it reaches 39.06 versus 36.35 and 35.63. And on AIME25 it reaches 18.5 versus 16.46 and 13.02. On AHEMC it is not the best average at 32, but it still gives the best average pass at 16 across the 3 datasets. So the gain is not coming from collapsed exploration.
What should we keep in mind after all of that?
The key takeaway is that RLVR works through a directional change concentrated on a few low probability, reasoning critical tokens. Measure that direction with delta log p. Use it to push decoding a little farther at test time. And use it to weight training toward the same rare tokens. The authors also note to limits extrapolation still needs both the base and RLVR models.
That wraps it up neatly.
This paper turns a descriptive analysis of RLVR into concrete ways to improve reasoning models. That is the main result, and that is the paper explained.